Okay. So, guys, I want to go over this homework with you. I want to answer your questions. And then, guys, we are going to use this as the second step in this process. So let's talk about where we're at so that we can make sure we're not overreaching. So, guys, last time in class, we started a 2-day conversation, about buffers. But guys, we didn't even use the word buffer until the very end of the day. And what we actually talked about was the common ion effect. And we talked about the idea that if we can take a weak electrolyte, acetic acid, it could be a base, ammonia, doesn't matter. If we've got a weak electrolyte, and if we add a salt that contains the conjugate ion to whatever that weak electrolyte is, guys, what we end up with is elevated concentrations of both the weak electrolyte, because the salt ion pushes the equilibrium backwards, so this goes up, and the conjugate concentration goes up, and we end up with a system that has elevated concentrations of both the weak electrolyte and the conjugate ion. That is a buffer. And we talked about the way that we are going to represent buffers. And guys, I told you that when you get to college, tune out what your professors tell you. And guys, as I was saying that to you last time in class, I'm like, wait, I have a video of the way they teach this in college, and I found it. It's really old. But guys, so are most of your college professors. And so this is the way they're going to teach this to you, with the understanding that I just really offended John and Eleanor. Guys, I'm going to show you the way they're going to teach this to you in college. And then you're going to appreciate all the more the last thing that we did in class, which was, I think, acetic acid, acetate ion. And we talked about that stupid analogy about the raiding hordes. And if there's an attack, who sacrifices and what's the result? Because it sounds childish, but wait until I show you the way they're going to teach this to you in college, and then you're going to get thankful. So, with that said, guys, questions on the homework? Yeah. If I said no, can we move on?
Sure.
21B. Go ahead. I just needed to reread it quickly. Yeah.
I was just wondering, how did it go? I was doing it at 12:30 last night.
Yeah.
So I wasn't computing anything.
Okay. So is your question focused around this part?
Yeah, I think it was going through the molarity of the pH.
Yeah, so, and guys, this is super important foundationally. This is a big idea. Don't miss this, because if you don't understand whether it's your question or not, guys, if you don't understand what we're about to talk about, what we're about to do, iRace boxes, is going to get really weird. So guys, join me. So what we've got here is we've got a situation where we are creating a buffer. But when we create this buffer, they don't tell us the molarity of the weak substance or the conjugate. They tell us volumes. They tell us that we have 85 milliliters of lactic acid, and then we have 95 milliliters of whatever the conjugate base is of lactic acid. But guys, notice the way I wrote it. You don't need to know the formula. The only reason you would need to know the formula is to know the mass. At the end of the day, it doesn't matter. So give it a name. If this is lactic acid, call the conjugate lac minus. You know it's negative because it's missing a proton. Just give it a name. But then the idea is this. And guys, this is the important bit. Guys, the only values that satisfy ice boxes are molarities. The only values that satisfy ice boxes are molarities. Explain to the person next to you why. There you go. All right, so guys, let's talk about it and sort of tie this up into a shared idea. So guys, we laid out this idea. We said that the only values that satisfy iceboxes are molarities. The reason is because equilibrium depends on rate. Okay? Guys, when we very first learned with the flippy tubes about rate, we said that Kc, or Ka, its products divided by reactants, guys, is equal to the little k value, the rate constant for the forward divided by the rate constant for the reverse. That's backwards. Reverse divided by forward. Doesn't matter. It's all about rate. So guys, if equilibria is dependent upon rate, and when we reach equilibria, the rates are canceling, the rates are the same, then guys, it makes sense that the only thing that goes in an icebox, because an icebox studies equilibrium, the only thing that satisfies the icebox are molarities. Are you okay with that idea? Okay, so then this. That's why we had to do this, because we needed to know the molarity. And so they gave us the volumes, 85 milliliters of 0.13 molar, 95 milliliters of 0.15 milliliter. So guys, the first thing we needed to know was moles. But then we need to convert that into a molarity. And guys, this is critical. These numbers cannot go in the icebox. Guess where they do go? iRace boxes. We're going to talk later. Guys, these values don't go in the icebox because they're moles. They're numbers of things. They aren't concentrations. So we have to divide by the volume. So guys, where the snap did 0.180 come from? 85 plus 95 divided by 1,000. Guys, that is also a very critical idea, because you're going to find out in the middle of your iRace boxes, you're going to be doing this math and converting moles to molarities. Now that we have the molarities, we plug them into the icebox, and then this should feel familiar. And a smile. A rather cheesy smile, but a smile nonetheless. All right. So, guys, what else? 20? Is it just one thing? Oh. Okay. Guys, so on number 20, I have spent a lot of time trying to explain this to students. I found a better way to explain it. Not the next lab we're going to do, but the one following. What we're actually going to do is we are going to start titrating strong and weak acids and bases with a pH meter stuck in it. And what you'll see is the lab that we're going to do does a really awesome job of showing you graphically what this question is getting at. And when you see it graphically, it provides such a better foundation for us to talk about this. So I'm just going to ask you to trust me on tabling this. But the bottom line is this. When you have a strong base or acid titrating a weak acid or base, for a very brief moment, it creates a buffer that almost immediately fails. You'll see it graphically, and then we can talk about it. What else, y'all? Yeah. Okay. Oh. Okay, this is a picture story. All right. Oh, man, guys, so I'm shopping for new books, right? 12th edition. You should see the 15th edition. It's exactly the same. It just has like they did like a refresh. The typeface is different and the colors have changed, but it's exactly the same stuff. That I don't know, because if the questions have changed, I'm going to be a busy beaver next year, because I'm going to have to redo all the solution sets. Yeah, because remember, the answers are in the back of the book, but it doesn't do you any good. You need explanations, which is why I spent the time to type all of this stuff. And if the questions are changed, I'm going to have to redo all of this, right? I know. Now all of a sudden you appreciate me. Mm-hmm. Say what? Well, any other edition has the possibility of being changed. So I may as well buy the most recent one, because actually the 14th and the 13th are more expensive because they're not in current print. Yeah. So the new one is the cheap one. And by cheap, guess what this book costs? $250. Yeah. Yeah, $250. Yeah, right? If you want to make a lot of money, sell stuff to schools. Oh yeah. It's crazy. Yeah. Again, they're more expensive. This is copyright 2011, so you can't find them. And when you do find them, they're either as used as these are, or they're through the roof expensive. They're like antiques. Yeah. Oh, they do that all the time, but the sad thing now is they actually don't give you a book. It's all online. It would kill me. Because Jared's got the answer, right? An iPad with a pencil, but my son is a junior pre-med, has never touched a textbook. That to me is crazy. Yeah, like, truth be told, I started stealing some of my old chemistry books and giving them to him so that he physically had a text to work with. Yeah, anyway, all right. Number 1, 16-1. Oh, 7, wait. We're in 17? How did that happen? Oh, because we're talking about buffers. All right. 17-1. The following boxes represent aqueous solutions containing a weak acid, HX, its conjugate base, X minus. Water molecules and everything else are not shown. Which solution has the highest pH? You ask.
I was just thinking, to me, like, the logic would be the more X minus there is, the more than HX is recognized. Which
Yeah.
means it's a stronger acid.
Yeah.
But then box 2 is the most of the X minus ions, and it sends it down.
So I think the thing that makes this tricky is they're removing all of the stuff that we might need in order to think about this, right? Water molecules, gone. Hydronium ions, gone. Cations, gone, right? So you're saying the answer is the middle one? So each box 4 molecules and a different amount of, so this is buffered. Okay, the box with the greatest concentration of X minus will have the smallest concentration of, meaning box 2. Okay. But that's not true. Box 2 has more X minus, right? Yeah, but I'm just thinking out loud with you, but I mean, if we've got all of this, so is it this? If we've got a lot of X minus, that means that whatever our acid is, the equilibria will shift. But wait, doesn't that mean it's protonating the most? Oh, so wait, is the assumption that the X minus is not just coming? Oh, wait, yes, no, that's the answer. And they said this poorly, but I think, Clara, the answer is this. Let me add some words to the question. The following boxes represent aqueous solutions containing a weak acid, HX, and its conjugate base from the addition of a salt. So, because if you look at this and just assume that the X minus is coming from the protonation of the acid, then that logic doesn't make sense. But if the source of your X minus, well, and it has to be because there's cations in there. And the presence of cations would tell us that there was a salt added, right? So that would then tell us, horrible question, but that would tell us that our source of X minus is also a salt. And so the more of that salt that we add, the more free X minus that we'll get, and the more the common ion effect would weaken the weak acid.
So how does the greater concentration of X minus result in more free H plus?
Less.
Oh, okay.
Yeah, right. So, shoot, hold on. Let me get in writing mode. Are you sure? Do you want to write it down? Do you want me to write it down? Okay. So this is what we've got. No. Stop it.
Your board said, never mind. The board does not like it.
I know. Why is it on? Just because that's where it sort of started. Okay. So we've got HX. So HX in equilibrium with X minus. I like that I'm just sliding as I write. So the idea is that the concentration of X minus is not exclusively from the protonation of this. We also added some cation X. And we know that because it says there's a cation present that they're not talking about. Sorry, I'm in your way. And so the idea then is that as we elevate the concentration of X by adding this, that shifts the equilibrium, Le Chatelier's principle, to the left, weakening the weak acid.
Doesn't that result in a higher concentration of HX than in the solution? Because all of these have the same amount of HX.
Maybe. I don't know. I mean, that makes sense. Anybody got ideas? 14. Does that mean we have to answer 2 hard things, or is this going to make this easier? Yeah, I like 14 better because 14 is just sort of cutting to the chase. I think at some level we understand the concept behind the common ion effect. I suspect that there are gaps in this because I agree with you that increasing this should increase that. Can we just celebrate that we understand the concept and not what? I don't know. Not to me. What makes sense? Correct, but Clara's question is, shouldn't there then consequently be more unprotonated HX? But there's not. Each one has 4. Right, I know, right? I think what we need to do is email Roxy and go, girl, what are you thinking? Mm-hmm. Right, and from that, yeah, and that kind of, we understand the concept, right? Are we okay? Okay, so guys, let's do this. Let's get this in the book. Oh, sorry, go, sorry.
I was confused about a couple, but I think we talked about 15B.
Okay.
Calculations and everything, but
Yeah.
how do you know, like, what
So when you say the equation, do you mean the icebox?
just like the equilibrium?
Oh, wait, this guy or this guy? Okay, so this is, and I'm probably putting words in, or I'm assuming your question. So the thing that makes this different is that we're now dealing with a base rather than an acid. So,
It tells me, like, there's in, well,
okay.
something, and then, I don't know, I just don't know how you know if it's like the base or an acid, and which one's first.
Well, this one has like a C, has a salt.
Right.
So like, that kind of makes me think it's getting added.
Yeah.
As like the opposite.
Yeah. Is that okay? Yeah. And so reading it out loud, it says a solution that is this molarity in trimethylamine, and thankfully they give us the chemical formula. They would always do that. But we look at that and we go, oh, look, nitrogen. And then 0.1 molar in trimethyl ammonium chloride. And I love that they're one right underneath the other. But if we compare these things, the dude below is, as you said, I think insightfully, that we've got a chloride, and that speaks to us of salt. But if you ditch the chloride, like literally for me, it's helpful to put my finger over the chlorine, and you're left with what is above plus a hydrogen. So that would tell us that that's our conjugate acid to that weak base. So at that point, we can come here and we can go, okay, nitrogen, that's a base. We always have to include water in ice boxes for weak bases. Then a hydrogen goes to this and forms this with chlorine as our salt. And then we get OH, which forms our base, and then we icebox from there. Is that okay? You sure? We good? Okay. So guys, grab another sheet of paper and let me get this recorded. And guys, don't let me make the same mistake again. Remind me to resume. Okay, so guys, here we go. Today what we're going to do is we are going to talk about titrating buffers. So guys, as we do, what I want to do is I want to bring us back to where we started. I know that this is redundant to the notes that you took last time, but I'm going to strongly encourage you to write this down. So guys, join me at the screen. Let's go white. And then guys, let's talk about this. So guys, you have absolutely no frame of reference for why this is helpful. I'm about to show you. So guys, let me ask you a question. We're gonna create a buffer. Would you rather us use a real world example like acetic acid and sodium acetate, or would you rather go HX and X minus and then our salt would be NaX? Real world? Okay, so write it down with me. So, and again guys, if you can switch colors, why not? So skip down a little bit. CH3, COOH, in equilibrium. So guys, we've got this. And then maybe switching to blue, because I can do things like that. So guys, let's take this and let's turn it into a buffer. So first of all, what does this look like if you sneak up on it in my stockroom? It looks like a bottle of vinegar, largely because it is a bottle of vinegar. So guys, this is a bottle of vinegar, and bottles of vinegar are not buffers. Elizabeth got us thinking about that last time in class. But guys, this is not a buffer. This is a weak acid. It does not function as a buffer. So what do we have to do in order to buffer this system? We need to add a common ion, sodium acetate in this case. And then guys, at this point, and I don't know how to represent this, so I'm just going to do something maybe like this. We have an elevated concentration of this, and we have an elevated concentration of this. Once we create that situation, we now have a buffer. And guys, what do buffers do? They resist change to pH. So how do we change pH? We add acids and we add bases. Now I'm really glad that we did this as a real world situation, because I'm realizing the real world situation is actually this example. So guys, now let's again put this in context. We take a bottle of vinegar, we dump in sodium acetate, hooray, we created a buffer. And then guys, at that point, we use that buffer as a solution that resists change to pH, so we attack it. And guys, when we say attack this, it really means titrate it. Titrate just means add in an orderly fashion. So guys, we're going to titrate our buffers with strong acids like HCl, and we're going to titrate our buffers with strong bases like NaOH. The question that we need to figure out is, how do they respond? Well, guys, if we add a strong acid like HCl, the chloride is the spectator. So we're dumping HCl into this bottle of vinegar. And guys, what we're doing is we are keeping our eye on the concentration of hydrogen ion, because that's what pH measures. So as we add the hydrogen ion, who steps up and attacks that hydrogen ion? The acetate ion. This acetate ion goes, I got this. I'm negative. That's positive. I got this. I'm going to lay down my life, and I'm going to sacrifice in order to grab these hydrogens and turn them into unprotonated acetic acids. But guys, all the while, notice that none of these hydrogens have made this go up. That's what buffers do. You okay with the idea? Now guys, what if we go the other direction? What if we add sodium hydroxide? Well, then it goes the other way. The acetic acid goes, I got this, and it starts handing protons to the OH, and when that happens, the product of that is now acetate ion. But guys, what is the other product as the acid gives hydrogens to hydroxide? Water. And so guys, our side product is also water. But guys, compared to the amount of water that this reaction is happening in the first place, we don't worry about the water that's produced. But guys, the idea is this OH does not attack this hydrogen, and as a result, the pH doesn't change very much. Guys, what questions do you have about that? Great question. And actually, I'm going to let this ridiculous video try to explain it to you. Yeah, but it's a great question. Why is it that when we add hydrogen, why does the hydrogen attack the acetate? And when we add hydroxide, and this is what the video's about, when we add hydroxide, why does the hydroxide attack the acetic acid and not attack this, which we actually understand to be hydronium ion? The video is going to take a swing at it, and then if we still need to talk, we can. It's a really good question. Go ahead. But why? Fundamentally, what is it about the acetic acid that makes that true? And that's the question we need to dig into. Go ahead.
Why does it need to be a common ion? Why can't you have just a weak acid?
That's interesting. Oh, so maybe the weak acid, and if it's a conjugate not of that weak acid, they might react? Honestly, Jonah, I don't know. That's a fascinating question. Why? I mean, I think you're onto something there, that it could create some interesting side reactions. But I'd need to camp on that for a second. It's a really insightful question. I'm just not sure. Sure, but couldn't this be a relative concentration of nitrite? Yeah, I'd like to play with that. Let's not run down, it's not a rabbit trail, but let's not run down it now. Okay, so guys, now we need to talk about some things before we get into this. So, the way that we're going to talk about this, and guys, again, your professors are not going to talk about it this way. But the way that we are going to talk about it, because conceptually it's easier and the math becomes more simple, is, guys, we are going to talk about this as a two-step process. And it ties back into an observation that Jonah made last time in class. So, guys, what you're going to see, and I'm going to try to denote this with different colors. That'll work. Guys, what you're going to see is this. we are going to break this chemistry into two different parts. And I'm going to sort of make a mess in our diagram. Please don't write this down. So guys, imagine this as a story. So we've got a buffer, and that buffer is sitting there contently. You got your thing of vinegar, you've added the acetate ion, and that buffer is at peace. That buffer is at equilibrium. And then we add, let's say, a strong base. And guys, as we add the strong base to the buffer does its buffer thing, and the strong base kicks the crap out of that buffer, that equilibrium system. And guys, literally what happens is for every one of these that gets added, one of these dies, one of these is born. And guys, that is not equilibrium. That is not rate dependent. That is quantitative chemistry. For every one of these that we add, one of those goes away and one of these gets formed. But guys, you know, in the world of chemistry, we don't count atoms by ones or twos or tens or dozens or thousands. What units do we use to count atoms? Moles. Guys, this chemistry in green has got to be in moles. But then what happens is this. Once we are done attacking the buffer and the moles-based quantitative chemistry is over, then it's like this village is trying to come back to equilibrium. And they're sort of looking around at the damage and they're going, whoa, that was a rough go. But now this is too low. We're not at equilibrium anymore. We've been at war. And this is too low. And this is too high. And now the system is going, okay, we're done dealing with the attack. Now let's go back to equilibrium. And so guys, if this goes back to equilibrium and this is too high and this is too low, which direction will the equilibrium shift to come back to equilibrium? To the left. But guys, now we're talking about equilibrium. So now we're talking about rate. So now what kind of units do we need? Not moles, we need molarities. So guys, the way that this is going to work is we are going to start by doing some quantitative math. And that will be in moles. That's the butt kicking. Then guys, once the butt kicking is over, we are going to do some equilibrium math as the system tries, well it does, as the system comes back to equilibrium. But guys, the units are different. This is in moles and this is in molarity. So guys, this is the way we're going to build this into a new box. We've got I and we've got R. You don't need to write this down. We're going to do it more later. I is your initial number of moles. R is the butt kicking. Guys, this is the amount that got reacted. And how much got reacted? How much of this did you add? Because every one of these that you add, one of those dies and one of those gets formed. So guys, the R is for reacted. Then the ACE is ACE. And guys, the ACE is where we start doing the equilibrium math. So A is for adjusted. The adjusted molarities. What did the adjusting? This. The molarity of this went down and the molarity of that went up. So we've got to calculate our adjusted molarities, then change and equilibrium just like a regular icebox. Do you get the idea? Okay. So guys, this is what this looks like in college.
Well, had an interesting look at a buffering system in the blood in the human.
This is what Barbara used to look like a couple generations ago. The only difference is they got students involved and tortured them into pretending like they're actually interested in what's going on. Ready?
Blood. Let's look at another buffer system, namely acetic acid sodium acetate.
All right, so acetic acid sodium acetate buffering system. We're going to call her, this is Bill and Julie. Go, Bill.
Elaine's going to help me analyze it.
Oh.
Based on this question, Elaine, what's going to happen
Okay, it's actually Elaine.
in this buffer system if we add a strong base such as sodium hydroxide?
Okay, well, you...
So the question is Elizabeth's question. What happens when we add sodium hydroxide? Elizabeth's question was, why does it attack the acetic acid? Here's the answer.
Going to help me analyze it. Based on this question, Elaine, what's going to happen in this buffer system if we add a strong base such as sodium hydroxide?
Okay, well, we'll use the 5-step method using the Bronsted-Lowry theory.
The 5-step method. That sounds fun.
Good idea.
First, we listed all our species and...
Okay, so guys, this is the way they're going to teach this to you in college. They are going to lay out all of the ions. You've got acetic acid, you've got sodium acetate, you've got sodium hydroxide, and water. It gets worse.
We're going to figure out which is the strongest acid and the strongest base, and acetic acid is the strongest acid and hydroxide ion is the strongest base. And the hydroxide ion will accept a proton from the acetic acid in the buffer, which will give us the acetate ion and water.
Now guys,
But
you
hydroxide-
understand that all of that is the chemistry that we write in blue? Would you rather write it in blue, or would you rather have to do all of this, right?
Or sodium hydroxide is a strong base, so would this be a quantitative reaction?
Good guess. It is indeed a quantitative reaction, and that's why we can put this quantitative arrow.
So guys, quantitative reaction, that's the I and the R, the initial and the reacted. Remember we said that it is quantitative? This is me trying to help you make sense of this ridiculousness.
Now, the other thing to notice about this system is as the base is being added to the system, something's going to happen to the concentration of the acetic acid and the acetate ion. And namely, the acetic acid, the concentration of the acetic acid is going to decrease over time because it's being used up reacting with the hydroxide ion, right? But the conjugate base that's being formed, which is the acetate ion, the concentration of it is going to increase. So this ratio here is going to decrease over time.
Did you notice that she actually has no idea what he's talking about? He keeps saying, right, okay, giving her answers, and she's struggling to just point at stuff. But guys, these ratios of up and down, do you understand those are our green arrows that we drew up on the screen? This is the difference between good and mediocre teaching. Again, it's called college.
Now, what's going to happen to the pH in that system as we add a base?
The pH will increase.
That's right. Now, it increases slightly, but it still increases. We can get a really excellent look at that if we look at a titration curve that we generated with
Guys, this is what we're going to do in lab.
that titration apparatus over there in the computer interface. And so here it is. Now, what do you notice about this curve?
Okay, well the pH started off at 5 and it just slightly increased.
Slightly increased. Notice, this is what we say about this. We say that this buffer is very efficient at resisting changes in pH, especially at relatively small amounts of acid, or in this case, base, are added to the system.
Okay, well it increases right there, but
Good.
is that when more base is added?
Close. The base is continually added at a steady rate. But what do you think's happening in the system at this point when the pH jumps?
Okay, the acetic acid is being reacted with the base here,
Right?
so it decreases.
Until what point? The concentration of the acetic acid is going to decrease until there's
No acetic acid.
no acetic acid left, and all you're adding to the system is hydroxide ion.
Have we had enough? I know, right? I know. But guys, I know, right? But guys, the long and the short of this, guys, is you're going to be generating these graphs real time in lab. But it is important that you understand what's going on here. So I'd like to talk with you about it briefly. So guys, what we've got here is we've got a buffer, and we've already identified the chemistry. So let's talk about it over here. So guys, you understand what we're talking about is the bottom of this, right? We're adding sodium hydroxide to this system. And remember, we've already talked about the idea that this is quantitative chemistry. You add one of these dies, and one of these gets created. But guys, where does this game end? Where does this chemistry eventually have to stop? When it runs out of acetic acid. Guys, when we run out of acetic acid, if we have 1,000,000 acetic acid atoms, that's not even close, we talk in moles, right? But guys, if we have 1,000,000 acetic acid molecules and we add 1,000,001 sodium hydroxide molecules, we just destroyed the buffer. It's like an army that runs out of soldiers. And the minute your army runs out of soldiers, the village gets overran. It's a good analogy. Guys, that is what is happening right here. That village just ran out of soldiers. This buffer just ran out of acetic acid, and at that point, it's Katie bar the doors, and actually what's happening is the pH is jumping immediately up to where it would have been had it not been buffered, and then it just keeps on going up from there. So guys, all of this means that these buffers have what we call, oh shoot. Why do you guys laugh at me so much? It takes a long time for feelings to heal. You guys know that, right?
You make us cry.
I make you cry. That's right. That's fair. I'm not telling you because you'll laugh at me. It's a good thing I like you guys, or I think I'd probably hate you. Hey. He established the baseline for angry talk, right? All right. Okay, so guys, actually we were surprisingly close to having enough copies. Yeah. Sorry, you're welcome. It's like, yeah. Oh, there's the mistake. Okay. So, here we go. Okay, and then... Okay. So guys, join me on slide number 2. And guys, sorry I didn't have the chance to put holes in these for you. We can do that later. Yeah, let's not do that now. We need to plow forward. So guys, the idea is this. Let me quit out of this and clear out of this. And guys, I'm just going to throw this all up for you. So we talked about this idea, and again, this is in your notes. We talked about this idea where the village runs out of soldiers. Guys, there's a technical term for that, and it's called buffering capacity. So guys, join me up at the screen. So when we talk about buffering capacity, the idea is that a buffer is a system that absorbs acid or base without an appreciable change in pH. But guys, its ability to do this depends on how many soldiers it has. So guys, looking back at this, the more that we can elevate this and the more that we can elevate this, the stronger the buffer is. So keeping with that thought, guys, if we have two buffers, if we have a buffer that is 1 molar in acetic acid and sodium acetate, or we have one that is 0.01 molar in acetic acid and sodium acetate, guys, two interesting questions. First of all, this: which one's the better buffer, the bottom or the top? The top. It's got 100 times more soldiers. Does that make sense? But here's the weird bit, guys. What is the pH of these two solutions? They're the same. And guys, if you're not sure why, please don't try to write this down with me, but if you're not sure why, Ka is equal to CH3COO minus H plus CH3COOH. So guys, what do we know about the concentration of this and this? They're the same in both examples. These go away, and at this point, the concentration of hydrogen is equal to Ka, so pH is equal to pKa. Remember when we talked about that last time? So guys, the pHs of these are the same, but this one's a better buffer because it's got more soldiers. Good? Okay. All right. So guys, with that said, is there anything else interesting on that slide to talk about? Same. Good there. Okay. Then guys, also when we talk about buffers, another important thing to talk about is pH range. So guys, do this with me. Going back to this math, join me at the screen. Given the buffers that were up on the screen just a second ago, we established the idea that they have the same pH. Guys, let that settle down. They have the same pH. Whether it's 0.01 molar in both or 1 molar in both, they have the same pH, right? Yes? What is the pH? It's pKa. So guys, this leads us to a really interesting idea. Say that we want to build a buffer that has a pH of 3. How do we do that? And guys, the answer is this. We grab a pKa table and we find a weak acid. Why isn't that writing? Oh, guys, we find a weak acid that has a pKa of 3. And then we add the conjugate base salt. But this, when is pH equal to pKa? What has to be true? These molarities have got to be the same. So guys, this is how you build a buffer. You're like, hey, yo, I want a buffer at pH 3. You grab a pKa table. You find a weak acid with a pKa of 3. You get some of that. Then you get the conjugate salt, dump the same molarity into that container, and now you've got a buffer that will be at the pH you want because pH is the same as pKa if the concentrations are the same. Go ahead.
So we only see one pH, but so do both of them add up to it, or are they just I'm kind of...
I'm not sure what you're adding up.
Okay, so those two are the same pH. Is it just that is the pH of the solution?
Okay, so let's do this. Boom. That might have been a rough transition. Okay, so let's go back to this. So we've got these two solutions, right? And are you comfortable with the idea that the top one's a better buffer because it's got more stuff? Okay. And are you comfortable with the idea that because these molarities are the same and because these molarities are the same, their pH will be the same? Is that okay? But not only is their pH the same, their pH is equal to pKa. And the reason is because Yeah, because the molarity of the weak acid, which is in the denominator of the fraction, is equal to the molarity of the conjugate ion, which is in the numerator. So these cancel out, and we're just left with hydrogen ion concentration. But hydrogen ion concentration is equal to Ka, so the pH, the negative log of hydrogen, is equal to pKa. Is that okay? You all right with that? Okay, now this. Gosh, John, I'd really like you to go into lab and build the buffer, but I would like for you to have that buffer at a pH of 4.74. So you go into a book and you find a weak acid that has a pK of 4.74. Oh my gosh, it's acetic acid, because it is. So the pKa of acetic acid is 4.74. And then you're like, oh my gosh, I'm going to get me some 1 molar acetic acid, and I'm going to dump in enough sodium acetate to make that 1 molar also in sodium acetate. And hey, yo, I now have a buffer, but that buffer has a pH of 4.74. Does that make sense? Okay, now what about this? Now imagine that I came to you and I said, hey, John, I would like you to build a buffer that has a pH of 4.8. Okay? Yeah, so what you do is you find a weak acid that's close. So now we're going 4.8. So this is 4.74, so we're in the ballpark, right? But we're not exactly there. So how do we make this 4.8? Well, that means we need a little less hydrogen ion, right? So how do we get a little bit less of this? We add a little bit more of this. And if we add a little bit more of the acetate ion, then it'll drive the equilibrium to the left a little bit, and it'll decrease the concentration of hydrogen ion, increasing the pH a little bit. And we can do that math with an icebox to figure out how much more of that we need to add to get it right to 4.8. Is that okay? Can I make one more point and then answer questions? So John, then, and I keep, guys, you know I'm talking to all of you, not just John, but then the interesting question becomes, how far can you stretch this, right? So yeah, if you've got a pKa of 4.74, you can go to 4.8, but could you go to 6? And the answer is no. So where is the limit to how far we can stretch a buffer away from pKa? And that answer is actually in these slides. So when we pick a buffer, we pick an acid or a base with a pKa close to our pH. But then we can only stretch this by about a power of 10. So if acetic acid has a pH of 4.74, we could push that to a buffer that has a pH as low as 3.74 or as high as 5.74. But once we push past a concentration gradient of about a power to 10, it doesn't buffer effectively anymore. Is that okay? Now what questions? Yeah. Absolutely, but praise the Lord, we don't have to do that. Yeah, because honestly, and you probably, at that point, you have competing equilibria, and you end up needing calculus to evaluate the way one impacts the other. Yeah, go ahead.
So, in the like situation are you adding that to like just
Is that helpful?
like container, or is it you're starting with one and you're putting it just?
Doesn't matter. So really, in this case, and we're going to go do this in lab, but in practical terms, your vinegar doesn't come as a solid, right? Acetic acid actually is a crystalline solid when it's not dissolved in water. But when we start with vinegar, we typically start with a solution, and we know its molarity. But then the sodium acetate is a crystal. So we would have to do the math that says, let's say for easy numbers, we have a liter of vinegar. And if we want to make it a 1 molar solution, then we need to know the mass of a mole of sodium acetate. So we figure out the molar mass of sodium acetate, weigh that out, dump it in there, and then we've got a buffer at equal concentrations of acetic acid and acetate ion.
So when you're going to find the pKa,
Mhm.
is that of the acid or of the conjugate?
No, because remember, great question, but remember, Ka values are for weak electrolytes, and by definition, the source of our conjugates are always soluble salts. They don't have Ka values because they break apart completely. They're strong electrolytes. So the Ka value that you're looking for is always, it's always the Ka value. It's always the Ka value for the weak guy. It's not, there is no Ka value for sodium acetate because it breaks apart completely. It doesn't reach equilibrium.
Okay, so if you've already been given the vinegar,
Mhm.
there's no way for you to adjust that pH past the one range of 3.7.
No, yeah, good question. So you could. I mean, you could, so say that this has got a pH of say that this has got a pH of 4.74. You could drive that down to 0 by adding gallons of hydrochloric acid. You could drive it down to 0, but then it's not a buffer anymore. So what we're saying is, yeah, if they just handed you sodium vinegar, there's a reasonable range within which you can do this, and it's 1 above or 1 below pKa. You can go beyond that, then it's just not a very good buffer. Is that okay? Okay. All right. So guys, with all,
If you act like concentration, whenever you go 1 pH above, and then you add a bunch of hydrochloric acid or whatever.
hold on. So above, so we've made it more basic, but now you're adding an acid. Okay.
Now you're adding the acid, so it drives the pH back down.
Mm-hmm.
It's not a very good buffer. Was the buffer even more effective as you add more hydrochloric acid?
No, so the hydrochloric acid. Oh, I see what you're saying. It's sort of resetting it initially, but understand that thing that is left would no longer be as effective a buffer because you've further thrown the equilibria out of whack. So buffers, they're fragile things, and so they're strongest when they have lots of both. There's nothing else inside of them mucking them up, and their pHs are close to pKa. That's when they're at their most stable. Anything that happens to throw those things off weakens the buffer. Is that okay? You guys good? Okay. So, guys, let's do this. I've got such a mess here. If you want more support on how to do iRace boxes, guys, it's all right here. I'm not going to read back through this with you because this is where we started. Here's what we know. When we attack buffers with strong acids and bases, guys, we've got a quantitative step done in moles. It's the butt kicking. Then we've got a qualitative, not qualitative, we've got an equilibrium step, which is the buffer coming back to equilibrium, and that's done in molarity. And that's what the iRace lets us do. We've got the I and the R, which is in moles. That's the quantitative butt kicking. Then we've got the ACE, which is the coming back to equilibrium after the butt kicking is over. So guys, we're going to do this in the next 10 minutes, and then we're gonna call it a day. You ready? You've got this in your notes. All right, you ready? I wouldn't write this. Well, you've got it in your notes, but guys, you're going to need room to write. Do you have a back? Do you have a clean spot? You're going to want to write this down. So guys, you ready? Reading the question. We just built a buffer, and again, we're using familiar friends. Guys, we just built a buffer that's 100 milliliters of 1 molar 1 molar acetic acid, 100 milliliters of 1 molar sodium acetate. There's the Ka. Guys, a question that's not even on the screen. What's the pH of this buffer? 4.74. So guys, I just threw up 4.74. How do we know it's 4.74? Take the negative log of 1.8 times 10 to the negative fifth. Remember and guys, these are things you got to keep track of. So if the molarities are the same, and if the volumes are we have equal molarities. If we have equal molarities, pH is equal to pKa, and the negative log of 1.8 times 10 to the negative fifth is 4.74. So as a starting point, we know that the pH of this is 4.74. Now, question number 1. What if we add 50 milliliters of 1 molar hydrochloric acid? Guys, do this with me. The first thing we need to do is we need to represent our buffer. You have the question in front of you, so I'm going to go clean screen. So guys, the first thing that we need to do is we need to represent our buffer. Do this with me. a little lower. CH3COOH is in equilibrium with CH3COO minus and H plus. Now guys, this I race, watch. IR, skip a line, ACE. You'll see why, yeah, I can get it in there. Skip a line. Okay, so now guys, before we even get into this, let's talk about the chemistry. I don't remember. Are we adding acid or base?
We're acid.
Adding acid?
Yeah.
Okay, good. So, let's go red for just a moment, and let's do this. We're adding hydrogen ions. So guys, which way does our arrow go? Who dies? Who gets formed? Does the arrow go left or right?
Left.
The arrow goes left. So guys, this is the butt kicking. So now what we've got to do is we've got to quantify the butt kicking. So guys, butt kicking is quantitative. So now what I'm going to do is go over here to our slides. And guys, this is what we need to do is a secondary calculation. And it looks like this. To do butt kicking, we need to know moles. But guys, we have milliliters and we have molarities. So we've got to go like this. 100, oh, we don't even have a significant digit. So guys, 100 milliliters, 1,000 milliliters is 1 liter. 1 liter is 1 mole of acetic acid. So guys, we do that math, and how many moles of acetic acid do we have? 0.1. So guys, super sloppy with significant digits, but we're okay. Now guys, we need to do a similar calculation for our acetate ion, and you have to show this. But guys, do you see that it's exactly the same math? Is that okay? Okay. So guys, taking that information then and skipping over here, we now know that this is 0.1 moles. It ain't molarity. It's 0.1 moles, and this is 0.1 moles, and this ain't none. So guys, now we've set up our buffer. Now we're going to do some hydrochloric acid butt kicking. And if you go back here, guys, our hydrochloric acid butt kicking is 50 milliliters of HCl. 1,000 milliliters, 1 liter, 1 liter. Love that I chose ones. So 0.05 moles of hydrogen ion. Did I do that math right? Hooray! Again, guys, you got to show this calculation. Now bring that over here. I'm gonna switch to red. Okay, so now, guys, this. How much damage was done to this buffer? 0.05 moles of damage. So, guys, our reacted portion of this is 0.05 moles and 0.05 moles. That's the butt kicking. By the way, guys, this is a buffer, right? This dude ain't changed. But now here's the question. Which goes up and which goes down by 0.05 moles? Well, guys, remember, these are the guys that die, and these are the guys that get born. So this is a plus, and this is a minus. Okay, now be careful how you use your space. Guys, this then becomes... Oh, we can just do this. Wait a second. No, let's do this. Okay, so in your extra line, 0.15 moles. In your extra line, 0.05 moles. And then 0. Whew. Guys, the buffer survived. It didn't break. It didn't fail. How do we know it didn't break? It didn't fail. We got some left. But guys, now the carnage is over. We have accounted for all the hydrochloric butt kicking that's going to happen. Now this buffer is going, all right, we made it. Let's get back to equilibrium. But guys, this new equilibrium, when we talk about it, we're now thinking equilibrium chemistry, so we're thinking rates, so we're thinking molarities. So we've got to take these moles and we've got to turn them into molarities. How do we turn mole into molarity? We divide. But guys, what we need to know now is we need to know the volume. What's the volume? 250 milliliters. 100 plus 100 plus the 50 from the acid. So guys, we divide this by 0.25 and we divide this by 0.25. And that is definitely calculator land for this kid. We will in just a moment. So guys, I get, being sloppy with significant digits, 0.006 molar, and 0.05 divided by 0.25, 0.2 molar? Wait.
I think it's 0.6.
Yeah, what? I'm like, that makes... Oh, I missed... Okay. Whew. About had a moment there. Yeah, I'm like, that makes... Yeah, right? So 0.6? Like that better. Do you guys understand why that threw me? Because don't we know that this has got to be bigger than that because we made more of this? Okay. So now, guys, remember the end game. We want to know pH. And so, Jonah, this gets mathematically to the question that you asked last time about, doesn't the hydrogen go up or down a little bit? We're about to do little bit. So now, guys, these are our adjusted molarities. What adjusted them? The hydrochloric acid butt kicking. So now we're ready to go back to equilibrium. This goes down by x, this goes up by x, this goes up by x. So at equilibrium, we've got 0.6 minus x, 0.2 plus x, and x. So then, guys, forgive me for cutting corners, but you know the Ka expression. So 1.8 times 10 to the negative fifth is equal to 0.2 plus x times x divided by 0.6 minus x. Yeah, guys, my board is super struggling, which is approximately equal to 0.2 divided by 0.6x. And then, guys, we solve that for x, I promise you, Monday. So, guys, 1.8 times 10 to the negative fifth times 0.6 divided by 0.2, 0.00005? Is that what you got? Yeah. Then, guys, we go pH is equal to the negative log. Forgive me for being sloppy. So pH is equal to the negative log of that. So, guys, if we take that and go negative log, and boom, I get 4.27. Yeah? Can you confirm that? Is that okay? Okay, so guys, let's talk about whether or not this makes sense. What was the pH of the buffer before we got started? 4.74. And guys, look at what happened. We kicked the trash out of that buffer. We bombed that buffer with 1 molar hydrochloric acid and a lot of 1 molar hydrochloric acid. Guys, the pH of 1 molar hydrochloric acid is 0. 10 to the 0 is 1. Guys, this is no screwing around acid, and the pH only went down from 474 to 427. That buffer just did its job. Now, guys, you'll notice that on your paper, and we're going to be done in 1 minute. You'll notice that on your paper, there's another question. And guys, check this out. The other question goes like this. I think I'm out of luck when it comes to clicking. Guys, the next question says this. What if you take that same buffer, and what if you hit it with 0.1 molar, or I'm sorry, 1 molar sodium hydroxide? So guys, go back here with me, and I'm going to switch to green. No, yeah, the original solution. So guys, same volume, same molarity, but now it's OH. So guys, wow, huh?
Just draw little rectangles to make the H.
Can you write on the shapes?
I just want to make the shapes go away. So green. Okay. So guys, do you see it? If we reset the scenario, and if we come back and hit this with hydroxide, same volume, same molarity, guys, which direction does the arrow go now? To the right? So guys, what effect would that have on the math? This would become negative, this would become positive, and everything else is the same. Because we started with 50 milliliters of 1 molar HCl, 50 milliliters of 1 molar NaOH would have exactly the same impact, only in the other direction.
So like on the step C of this, would it still be minus 9?
Oh yes, yeah. So the strong thing impacts this, but once that system comes to this mucked up set of circumstances, which is represented here by the adjusted reality, if you will. Once you get to that adjusted reality, then it's just a simple icebox from there down. Which actually, Claire, and we'll finish with this. When they try to teach you to do this in AP, or I'm sorry, in college, they will have you write out everything, just like that poor girl had to do on the video. And then what they do is they have you try to figure out all of this math doing exclusively dimensional analysis. But it's dimensional analysis that includes subtraction and addition. And so you're trying to fumble and go, which one's my addition, which one's my subtraction, who's actually doing the chemistry? It's crazy. But they will teach you to do all of these side calculations that get you to this, and then they tag it all into an icebox. So when I struggled with this, I'm like, what if we could take this icebox structure and take all this ridiculous quantitative chemistry and keep it in the same structure in a way that it's easy to see the chemistry? And that's how I came up with this. So, but yeah, once you're done with the reacted part, this all flows the same. Yeah.
For me, it just have it as.
What?
I'm saying, well, so I saw for the pH, this one, I got 5.92, so it goes up, but
Yeah.
it would have gone down.
Okay.
Could we just add that instead of, so just subtract the two pHs and then add?
Yeah, you won't see a problem like this. So you'll see a problem like this, but you won't see what if you add this, and then what if you add that. Because frankly, we're limited on time, and they're not going to have you solve 2 complete iRace boxes. So that wouldn't be a corner that would even be available to cut. So, you guys okay? All right. You have the homework in front of you, right? Yep. Take a break.